analysis of a continuous beam with moment distribution method. When the A and C are fixed, B is a continuous support. So you can understand here the kinematic indeterminacy is equal to 1, which is theta B. So theta B is the unknown here. Now we can calculate the fixed end moments. So for these fixed end moments, MFAB is equal to, so this is already known that for the moment distribution method, the sign convention is anti-clockwise will be considered as negative, clockwise will be considered as positive. So minus WL by 8. So this is minus 100 into 5 by 8. So this is minus 62.5 kilonewton meter. MFBA is equal to plus WL by 8 plus 100 into 5 by 8, which is plus 62.5 kilonewton meter. So these are the fixed end moments of MFAB and MFBA. Now coming to MFBC. So MFBC is equal to minus WL square by 12 minus W is 50 kilonewton per meter is loading, L is 6 meters by 12. So minus 150 kilonewton meter. MFCB is equal to plus WL square by 12. So this is plus 50 into 6 square by 12, which can be taken as this is plus 150 kilonewton meter. So we have already calculated the fixed end moments. Now we need to consider the distribution factors. So distribution factors will depend upon the relative stiffness of the members. So in the previous classes, we have seen the distribution factors corresponding to the stiffness, relative stiffness of the members. So we will consider this as distribution factors. So this distribution factor, where you need to consider. So your beam is this one. In this one, wherever the joint is there you can consider the distribution factor. So as it is a continuous joint, continuous support, so at this point we need to consider what is the distribution factor towards BA as well as towards BC according to the relative stiffness of the members. So we have already written distribution factor. So this is at joint B. So distribution factor for BA is equal to, so relative stiffness of BA member by summation of the relative stiffnesses, summation of the relative stiffness at the joint. So at the joint, two members are meeting, so KBA plus KBC. So this is relative stiffness, we are writing it as I by L. So KBA I am calling, so this can be written as LBA or L1. So this is I by length of member BA plus I by length of member BC. So here I am writing it as I, as the moment of inertia is uniform. Otherwise, if it is varying, we need to consider it as I1 and I2. Now substituting the values here, so this will be I by 5 by I by 5 plus I by 6. So the value will be 6 by 11. DFBA is 6 by 11. Now DFBC is equal to KBC by KBA plus KBC. That is relative stiffness of the member to the relative stiffness of the total joint, members meeting at the joint, the ratio that can be considered as distribution factor. So this will be I by LBC by I by LBA plus I by LBC. So this is I by 6 by I by 5 plus I by 6, which will be considered as 5 by 11. So at any joint, the summation of distribution factors is always equal to 1. So you can consider here when you add these two terms, DFBA as well as DFBC. So that is DFBA plus DFBC, they are equal to 1. They are equal to 1. So at any joint, the distribution factors summation is equal to 1. So after calculation of these distribution factors, now we have to go for balancing the moments as well as calculating the carryover moments. So I will once again bring the beam here. So this is support A, B, C. This is loaded with 50 kilonewton per meter and the span is 6 meters. A point load which is acting at the center, which is 100 kilonewton, and this is 2.5 meters. This is 5 meters. Moment of inertia is I. Now just extend the lines to do the problem as per moment distribution method. Just extend the lines like this. At the joints just and supports, just extend the lines. Now in the first one, just left of the support A here in your notebook, write down the first one, that is distribution factor. So here this distribution factor will be written at the joint. So when you are writing at the joint, here you can observe I am just keeping a box here to enter the values of the distribution factor. Corresponding to BA, the value is 6 by 11. Whereas corresponding to BC, the distribution factor value is 5 by 11. And you need not write at A as well as at C, the value will be 1 only. There is no another member, only AB is there at support A, and at support C, CB is there. So obviously the value is 1 only, that's it. So now after this distribution factor, write down fixed end moments. Fixed end moments. So what are the fixed end moments? So here in this fixed end moments, the value of MFAB is equal to minus 62.5 kilonewton meter, and this is plus 62.5 kilonewton meter for MFBA. This is MFAB. Now here enter the value as of MFBC as whatever you got, 150. So this is with the sign you have to write it as minus 150. And coming to here for MFCB, the value is plus 150. So the values are written in terms of moments and the values are in terms of kilonewton meter. The values, they are entered in terms of kilonewton meter. Complete till now? So after writing this fixed end moments, now we have to do balance. So what does it mean by balancing moment? So just see the observe at the joint B. We know that what is the joint condition that is to be followed at support B. Whatever the moment, final moment of MBA, that should be equal to MBC numerically. That means the joint condition that is to be followed at the joint B, MBA plus MBC is equal to 0. So that is to be followed. But just see this one, this value is plus 62.5 and this value is minus 50. They are not equal. And what is the difference between them that is there? So here just see this one, this is minus 150 plus 62.5 and the value is now minus 87.5. This is the moment that is to be balanced or that is to be distributed between the members BA and BC. We have to balance this joint B as the numerically they are not equal. So how much the difference is there, that value we have to take it. Now if you calculate the difference, this is minus 87.5 and this minus 87.5, and now we have to balance it, so we have to consider it as plus 87.5. So you can't distribute this half of. According to their distribution factor only, we have to distribute the moments. So you can write down here it as balance B. So balance B is nothing but we are going to balance support B. So how we are going to balance support B? The difference of the moments at joint B and with the opposite sign and multiplying with the distribution factors. So the difference is 87.5 minus value. So take it as positive 87.5 and multiply with the distribution factor. So this will be plus 6 by 11 into 87.5 plus 47.72 kilonewton meter, and whereas here this is plus 5 by 11 into 87.5. So this is plus 5 by 11 into 87.5, 39.77 kilonewton meter. So we balanced B. When you are balancing B, here what happened, the support, just go to your theorem number 2. While writing theorem number 2, the moment M is there and this will be M1 and M2. This is M1 and M2. When the far end is fixed, according to our theorem number 1, so we have to consider a carryover moment. So the carryover moment for this one is when the far end is fixed. Once again, remember, when the far end is fixed, so we need to consider this moment, balanced moment, should be transferred to the far end, which is to be taken as 50% of the balanced moment. So in this, so you write down this one as carryover moment. So in this, whatever the value is there for span BA from B support to A, here the carryover moment will be, just give an arrow mark like this, and the carryover moment is plus 47.72 by 2. Automatically they are the shapes are changing, but however this is plus 47.72 by 2. Now from here and coming to span BC plus 39.77, this will also be carried over to the far end when it is fixed only. Remember, when it is fixed, then only the far end moment will be carried over, and here this value will be plus 39.77 by 2. I'm sorry, here the values, they are 39.77 by 2. So now, is there anything that we need to balance once again? After this, just check it. So We will write down the moments, final end moments. So final end moments, how we are writing? So just add the columns. So the moments are there here, minus 62.5 plus 47.72 by 2. So what is the value here? Now coming to here, we are adding for BA. So this moment minus 38.64 is the final moment, which is MAB. And this will be MBA plus 62.5 plus 47.72. So the value is MBA is 110.22 kilonewton meter. Now this one, MBC, and add the values. So minus 50 plus 39.77, and if you take it as minus 110.23. And now coming to MCB plus 150 plus this value is actually plus 39.77 by 2. So what is that value here? And with the obtained final end moments, we can draw the shear force diagram as well as bending moment diagram. Analyze a continuous beam using moment distribution method. Using moment distribution method, and this is the beam given. The beam is loaded with a UDL of 10 kilonewton per meter for span AB and 30 kilonewton meter for span BC. And you can understand here support C is a hinged support where the final end moment is equal to 0. Where the final end moment is equal to 0. Final end moment is equal to 0. Here nothing is given mentioned about the moment of inertia, so we'll take it as moment of inertia is equal. So in the first step, we'll calculate the fixed end moments. So keeps a heading fixed end moments. So MFAB is equal to minus WL square by 12 minus 10 into 6 square by 12. So the value will be minus 30 kilonewton meter. MFBA is equal to plus WL square by 12. So which will be plus 10 into 6 square by 12, which is plus 30 kilonewton meter. Plus 30 kilonewton meter. And this is for MFAB as well as MFBA. Now calculating for span BC. So the fixed end moments are calculated by considering the supports are as fixed. MF BC is equal to minus WL square by 12 in this minus 30 into the span of BC is 5 meters, so 5 square by 12. So what is this value? MFCB is equal to plus WL square by 12, which is plus 30 into 5 square by 12, so which is plus 62.5 kilonewton meter. Now in the next step we need to calculate distribution factors. So keep side heading distribution factors. So in the distribution factors, we are calculating at joint only, at joint B. So DFBA, at joint B there are two members are meeting. So DFBA is equal to, now see this one, just once again I am drawing the beam. This is your beam. So the spans are given as here, the support is there, here another support is there, the length is 5 meters here, this is 6 meters, moment of inertia is same. Now in this one, so this is for span AB, this is for span BC. Now just understand, when the far end is fixed, then only the stiffness will be considered as I by L. Otherwise, according to our theorem number 3, if you observe, the relative stiffness of the material got reduced to 75% of the value only. So that's why we wrote it as 3/4 of I by L. Just you can refer your notes and check it. So when the far end is fixed, then the relative stiffness of the member reduces to 3/4 of I by L. If the far end is fixed, then the value will be I by L only. So here I have to write down this as the distribution factor for BA will be KBA by KBA plus KBC. So here the KBA value will be written as here the far end of the support of the span BA, the far end is A, it is fixed. So this will be I by L1 or LBA, you can write down, or AB by I by LBA plus, so in this one KBC, so for span BC, the support C is a hinged support, either it is a hinged or roller, then it will be reduced to 3/4 of I by L. Just remember this is important. So the support, according to the support, when the far end is hinged, then the stiffness, relative stiffness of the member reduces to 75% of the value. So I by L, this is I by L is 6 by I by 6 plus 3/4 of I by 5.
10.
Value 10 by 19. So here once again I am repeating, remember this, when the far end is hinged, then the relative stiffness of the member reduces to 3/4 of I by L. It will not be considered as I by L, you need to multiply with 3/4. This is as per our theorem number 3. We have derived that one in the previous classes. So this is 10 by 19. So writing the distribution factor for BC, this will be KBC by KBA plus KBC. So this will be I by LBC. So here, what is the relative stiffness of this one? So you need to multiply with the 3/4 of I by LBC. by, you need to multiply with 3/4 of I by LBC by I by L length of span BA plus 3/4 of I by LBC. So this will be 3/4 of I by 5 by I by 6 plus 3/4 of I by 5. So what is the value of this distribution factor for BC is 9 by 19. So you just check it. When you add both the values, these values when they are added, then they will be equal to 1 only. That means the distribution factor at a joint, it will be equal to 1. Always it will be equal to 1. Now, drawing the beam. Once again, draw the beam. So this is A support, which is fixed. This is support B. This is support C. Length is 5 meters. Moment of inertia is I. Length is 6 meters. Moment of inertia is I. Just extend the lines. Otherwise, you can draw a continuous line also, no problem regarding the line designation. Now, the first one is distribution factors. So wherever the joint is there, they write down the distribution factors. So this is 10 by 19 and the value is 9 by 19. So just make a box here. So these are the distribution factor values at joint B for span BA as well as for span BC. Now after this distribution factor, write down the fixed end moments. So fixed end moments, what are the values of the fixed end moments? MFAB, we have already written the values here, minus 30, plus 30, minus 62.5, plus 62.5. So that is minus 30, MFBA is minus 30, sorry, MFAB is minus 30, MFBA is plus 30, minus 62.5, plus 62.5. Kilonewton meter. The units are in kilonewton meter. Now after writing down these fixed end moments, we have to balance the supports. So which support we need to balance first, that we should understand. So which support I need to balance? So here in the entire beam, first of all, before going to the joint, first wherever the simple support or the hinge or roller support is there, at that support, what is the known value? The moment at the joint is equal to 0. The moment at the joint is equal to 0. So as we know that moment at B at C, you know that this is a hinge support. At hinge support, the moment is equal to 0. So when the moment at this point is equal to 0, you have to make it to 0 by balancing. So in the first step, just see this one. When there is a roller support is there, this value is plus 62.5, but actually the end moment, it should be 0. So to make it 0, I am applying a balancing moment at C. So balance C. Why we are not balancing B? I am not doing balancing. Why? Because the priority will be given for the simple support. So how to balance that one? Idea is to make it to 0. To make it to 0, how much moment I need to apply? Here the moment applied is minus 62.5. So when I apply minus 62.5 kilonewton meter and when I add it, it will become 0. So the support C is balanced. But when we are adding, you can't add whatever the moment you want. With the added moment, with the balanced moment, it will be giving carryover moment. So the carryover moment will be there to the far end, which is fixed. So the carryover moment will be there. So this carryover moment will be there to the nearest support. So for the C, the nearest support is B, and it is a continuous support which can also be, which will be accepting the carryover moment. So this will be, so we know that according to our theorem number 1 in the moment distribution method, when a moment is applied and the carryover moment will be half of that moment applied, so this will be minus 62.5. So this minus 62.5 by 2. So that is the carryover moment. So when you are balancing this, now we'll, for the simplicity, what we will do is we'll just make it here a closed line. So just I will write down net moments. So net moments are nothing but just add the columns. So this is minus 30. Support A is not at all balanced. Support B, this is plus 30. And now the value is minus 62.5 minus 62.5 by 2. At support B towards BC, so the moment will be minus 62.5 minus 62.5 by 2. So minus 93.75 kilonewton meter. And you know that plus 62.5 minus 62.5, which is equal to 0. So these are the net moments after balancing C, and carryover moment is applied at B. Now just see this one. So these are the moments that is to be considered when you are writing these net moments, and we need to consider from here onwards. So here onwards we need to consider the balancing. Now in this one, plus 30 is there, minus 93.75 is there. We know that support B is to be balanced. Now we will see support B is to be balanced. So balance B. So when you are balancing here, now what is the moment that is to be balanced? So the difference here in between is plus 30 minus 93.75, and the difference is minus 63.75, and this is negative. So you have to take it as opposite sign, and this is plus 63.75. So this, just check it once again. Plus 30 is there. This is minus 93.75 is there. As per joint conditions, both should be equal, and numerically they should be equal, and when you add it they should be equal to 0. But here what happened, there is not equal to 0, and the difference between the moments is minus 63.75. Now to make it balance, consider the opposite sign, which is plus 63.75, and this 63.75 will be distributed towards BA as well as BC according to distribution factor. Now distribution factor comes into picture. To distribute this moment, you can't distribute half of the moments to make it balance. The distribution will be done according to their relative stiffness of the materials. So this relative stiffness depends upon the moment of inertia, length of the member, and the support, the far end support. When the far end support is fixed, the relative stiffness is I by L. When the far end support is hinged, the relative stiffness is 3/4 of I by L. So this is plus 63.75, and this will be 10 by 19 into 63.75. You remember this is positive, and this is plus you distribution factor multiplied with the difference moment between the joint at the joint. So plus 9 by 19 into 63.75 again. So with the decimal values, be careful. Now after getting this balance at B is balanced, but whatever the moment you are adding, so this will be giving carryover moment according to the far end support. So carryover moment. The next one is carryover moment. So in this, so what is the carryover moment? From this when the far end is fixed. So what is the far end here? A support is fixed. So half of the moment will be carried here. So this is plus 33.55 by 2. Whereas coming to here, this is plus 30.20, and here carryover moment will not be there. Why? Because the far end is hinged. Support A is fixed, that's why carryover moment is there from B to A towards BA, and from B to C, as C is a hinged support, already you balanced it, then once again you should not send the carryover moment. So the carryover moment will not be there for B to C. Now you write down, so further there is no need to balance anything, and you can write down the final end moments. So final end moments. So to write these final end moments, now this is minus 30. You should not go beyond the net moments. We are already calculated the value from here. So from the net moments, you add these values, minus 30 plus 33.55 by 2, 5 kilonewton meter, that is MAB. So I will write down the values here like this. So MAB is equal to minus 13.225 kilonewton meter. Whereas coming to MBA, so for MBA, so from this net moments plus 30 plus 33.55. So this is plus 63.55 kilonewton meter. So this is plus 63.55 kilonewton meter. This is MBA value. Coming to MBC, MBC is equal to minus 93.75 plus 30.20, which will be minus 63.55, and the value here will be 0. So minus 63.55 kilonewton meter, and this will be MCB is equal to 0. So these are the final end moments of given continuous beam. And further we can draw the shear force diagram as well as bending moment diagram. On one problem for your homework, take it. Analyze the continuous beam. Analyze the continuous beam by moment distribution method. Analyze the continuous beam using moment distribution method. So take this one. A is a fixed one. This is 80 kilonewtons point load is there. Another 80 kilonewtons point load is there. This is support B, and this is support C. 12 meters is the span here. This is 9 meters. Here the moment of inertia is I. Here the moment of inertia is 2I. And this is loaded with a UDL of 12 kilonewton per meter. So when one point load is there, we know how to do that one, that is minus WAB by L, and you can consider this as A is 3 meters once, as well as B is 6 meters. Then you can calculate WAB by L, W1 A1 B1 by L plus W2, okay, sorry, In this, how you will do that one? So this is, if you want, this is MFAB is nothing but minus W1 A1 B1 square by L square minus W2 A2 B2 square by L square. So that is nothing but minus 80 into 3 into 6 square by 9 square minus 80 into 6 into 3 square by 9 square. So then from this you can calculate MFAB. Similarly, MFB